Good morning, everybody. I'm Chiara Manzini. I'm an aerospace engineer who studied first in Milan and then in UNIGLO7. And thanks to my high passion for sports and my interest in giving an effective contribution to human beings, I'm highly interested in biomedical work.
Good morning to everybody. I'm Angelo Vitti and I am a biomedical engineer. Led by my strong passion for facility design, I decided to study first in theory and then in Milan. I've always been fascinated about the idea to work in the space. So when I was younger, I read a lot of stories about astronauts and their kids. I'll tell you about the context in which our gaze, then the state of the art to look at a starting point, objective we want to reach, and experiment stuff. Then my colleague will explain to you the experiment process, how we want to deal to critical mass and volumes, cost and risk analysis, and next step we are planning to do. But first of all, I want to start with a question that probably is in all your mind. How is it possible for those different words to get in touch? Those people are really different, and also really different are all their needs. But this is not true. They have something in common. Heart. Heart is what we consider the center of a person, where we channel emotion and what makes us perform all things we want to do. But heart is actually the first organ affected by consequences of our lifestyle. From the World Health Organization, we can see that cardiovascular disease are the first cause of death worldwide. And also, earthbound disease are very common. In fact, every year, about 300,000 earthbound replacements took place. And the number is expected to grow. In fact, due to the aging population and technological development, it is expected to rise up to 800,000 in 2050. But let's do a step back. Heart. From the physiological point of view, heart is our engine that takes care about pumping blood to the body. Earth valves have the role to guarantee the unidirectionality of the flow, maximizing the pumping effect. But when this feature is lacking due to the stiffening of liquids due to the gasification process, we talk about valve blockages. How to deal with them? Well, in the left way, with drugs. In other cases, with heart valve replacement. Nowadays, doctors have three different options of earth valve procedures: mechanical, radiological, and polymedical. All of them have different pros and cons, but doctors prefer to use the biological one because they mimic very well the behavior of the natural one. But also for these features, we have a problem with the classification process again. Early classification is also a problem for patients with LVAD device. In fact, the left blood pumped by the left ventricle in addition with the regular flow due to the action of the external pump causes the non-total opening of the valve, and so the problems with the so-called washing reflex effect. That is very important to avoid the calcium depositation. Of course, this is a long-term phenomenon, but this disease is increasing because this device is implanted now not only in a permanent way, but also in a permanent one. So, what about space within this context? It's well known that astronauts suffer from an higher calcium concentration due to the less loads on board. From the cardiovascular point of view, the system replies to the microgravity environment with a lower stiffness of veins and arteries, hypovolemia and hematocrit increase, and as a consequence, a blood shift in the lower part of the body. This stagnation of liquid causes the reduction of the venous return to the heart, and so the reduction of the stroke volume due to the starving effect. Those highlighted features are very similar to the ones we talked about the patient with LVAD device, and so we assume that also astronauts suffered from the non-total opening of the valve, and so from those evidences, in addition with the changes in the local fluid dynamics in the microgravity environment, we can expect that the classification process starts earlier and is faster also in healthy astronauts. This scenario is very likely because this is a long-term phenomenon, and longer and longer space flights are planned. So you can say that we can directly study this phenomenon on astronauts, but actually we can't, because we need very specific instrumentation to be placed in the ISS, and this is not feasible. In addition, we want to predict this phenomenon in order to think about possible countermeasures, so we need an accelerated process. So from the beginning we want to carry out our experiment in three different directions in order to obtain three different objectives, and so we decided to divide our experiment in three different phases. First, basal phase. We will record the movements of the heart valve in a cardiac cycle. Second, classification. With the help of the calcium phosphate solution, we will accelerate the classification process. And last but not least, low body negative pressure. This is a technique actually used to reduce the blood shift in the lower part of the body. So we want to understand if this technique is useful also in our case. How to manage all these things? Well, we need a mock-up simulator, but actually we can't use a standard one because of the specific constraint. So we have to build our own edge test. As you can see, this is a very simple scheme of our idea, but it contains all components we need. This is a test section with the heart valve positives and major sensor in order to understand the performance of the heart valve. A linear resistance and an elastic compliance to mimic the systemic behavior, low body negative pressure simulator, a tank with a calcium phosphate solution and a gauge sensor in order to manage the classification process, and a continuous pump plus a solenoid pinch valve in order to obtain the pulsatile regime. All components will be linked by silicon tubes, and the liquid in the circuit will be water with specific solute in order to have the same behavior of the blood in the microgravity environment.
Let's talk now about the experiment process. First of all, as my colleague said, there will be three different phases, but each of them will have three different statuses. The first one will be the configuration mode, use the setting of parameters. The second one, the acquisition mode, the storage into local memory, and then the third one, the transmission mode, in order to receive data and use them as a feedback to the configuration mode data. Now let's talk now about masses and volumes, which are, I would say, the most important parameters for the design, since they mean expressiveness, both in terms of, for example, cost and unities of SQSAT. I would address the pump and the high resolution camera as the most expensive one in terms of mass, whilst the pinch solenoid valve in terms of volume. In particular, we overestimated by now, since we are in the preliminary design, the volume. We would have quite a big bench test, but we hope to get up to 6 unities of SQSAT. And we are already trying to reduce the mass. For example, we already substituted the piston pump, which would be technically better, with a centrifugal pump giving constant flow, but connected to the pinch solenoid valve to give the pulsatile region. Then we can see the direct relation between the weight and the launch cost, which is the most important one, the foremost one, and covers up to 85% of the overall cost. But this result is already outstanding, since the other costs are basically paltry, as you can see. So our experiment is quite cheap, and we come to have it even cheaper. Then, risk analysis. Of course, the first one is the braking or failure of components, so the reliability of them. And for this, to avoid this, since there is no solution in space, we are going to build a lot of tests, hardware tests. Then other risks can be accuracy or calibration of the sensors or bad illumination, which could affect directly the data and output. And the supersaturation of the fluid, causing the precipitation of calcium phosphate in the porous material. By now, everything was done by only the two of us, without even a professor, so we realized that we need a team, and in particular, we already by now, 3 aerospace engineers, 2 biomedical engineers, 1 electrical engineer joined us, and we are currently looking for a management engineer and a telecommunication engineer in order to have quite an horizontal team. With an exchange of ideas from different fields, and in parallel we are running the funding searching, of course. Then there will be, of course, the more detailed design and with the test, as I previously said. But after the launch, there will be the data analysis, which is quite important, because from this we are hoping to get 2 important results. One, from the microgravity point of view, so to understand the relationship between microgravity environment and the Earth valves of astronauts, and trying to understand also the countermeasurements in the periods of the orbit, previously and after. But given the correlation with the patient with LDAD, we want also to analyze the geometry of the valvular prosthesis in order to have more resistant and more reliable ones in time. Okay, as you can see, these 2 different works can get in touch actually, and this is really difficult, but it's possible. So we as a team are the best example of this totally uncommon pair. Thank you for your attention.
Ladies, questions? Thank you for keeping the time.
You say that you can reduce the volume because it will be a very expensive experiment if you use all 12 to do 3x4U space station. So you can do it in 6 years already better, but if you still need to get the funding, how do you plan to go about getting necessary funding for this project?
Actually, we already found 2 postdoc students, one from London and another one from Ireland. I don't remember the name of the university, and they are really interested in this project. And in particular, the one from Ireland already found 10,000 euros that could be used for this experiment, and is also finding new links with other people, other professors, which are quite interesting. So yeah, we are going to this direction.
Professors normally are very poor, so they want to get the next funding. Can't go for that. Another question. You said that calcification is defined as the buildup of calcium in soft tissue. What is the link between bivalves and soft tissue valves? Both can calcify, it seems, but is the calcification process the same? Is it the same impact over time, or is it different?
Well, actually is quite similar, because heart valve prostheses, in particular the biological one, are made with the tissue from pork or from bovine ones. So the classification process in this type of tissue is very similar, and so we can easily understand if the impact using the calcium phosphate solution, because this solute is very important in the calcification process, also in humans.
Okay, so it's also soft tissue, the
Yes.
else also it's just
Yes,
formed
yes.
out.
Yes.
Okay.
Hi, thank you for the presentation. One question I had is with the concept of your design, with your tubes and the sensors and the pump and so on. How representative can you consider that when you would be comparing, for example, with heart valve and the whole heart system of an astronaut? In how much can you consider this as a scientific model to compare?
Because actually our current procedures are tested with standards in order to be used in the implant surgery. So we have standard indexes to compare our results that we can get from this experiment to the ones we already have from the standards. And also we want to compare the experiment done in the microgravity environment with the same bench test in the heart. So we can, by the link between these two different data, we can understand the effect on the microgravity on the output.
Can you say a bit more about the low body negative pressure simulator? How you simulate that and why that phase? I think the mission duration for that part is 7 weeks. And I didn't understand what it is that you simulate that requires 7 weeks to see an effect.
Okay. So the idea is that the basal phase have a standard of the behavior on a microgravity environment. Then we have the tension force phase solution in order to have the classification process. And then even we have the low body negative pressure simulator, the classification process will run. So the low body negative pressure simulator is an actuator and a mechanical actuator, and that causes the increasing of the flow in the continuous pump again, because this is actually the meaning of the low body negative pressure device. So to reduce the stagnation of the liquids in the lower part of the body. So by pushing the tubes, we want to increase the flow from the continuous pump, and in this way reduce the stagnation of liquids. This is our idea to simulate this technique.
And about the 7 weeks, because I suppose that effect on the fluid dynamics would be relatively quick.
Because we need time to understand if this effect impact in the classification process or not. So we need time in order to have the classification.
And one last comment picking on what Herman said. So indeed, mass is an important factor in the cost, but volume is also an important factor in the cost. So I think as of now in the cost figures, that's not something that is considered yet. So the weighing of whether you can make it 6U or smaller would be important.
I think we can get one last question. Okay, I was just going to ask, you last question? I don't know if it's the last question. My first question. Are you planning to build a ground equivalent of Vantage at the same time?
Yes. We don't say that, but maybe we have written in
in our university, we plan to build it in Polytechnic of Milan.
Yes.
For example, we could also get some parts from Polytechnic of Milan. The Arctic valve, probably we are going to get it from them.
In this week said the main thing is to make it as compact as possible, because you're paying by the unit as well as by the kilogram. Your cost estimate is way off as a result.
Okay, thank you very much.